Good morning and good afternoon, everyone. My name is Sukumal Kirisin. I'm at Ksat Science University, and I'll be your moderator for this morning, your morning, our afternoon. Thank you very much for the author who kindly joined us for Q&A sessions. The first paper is Falcon, right? Let's take turns from each part, taking questions and answer from the authors. Is there any questions from our part on this paper? Okay, please introduce yourself and then ask questions.
Okay, so I'm not sure that okay. Good afternoon and good morning for the Spain side. My name is Waramed Prunjaren. I'm graduate student from the Thailand. So I have a question for the Falcon work. Okay, so the first question, this work is not new. So I heard this protocol before in 2023. So I want to know what had changed since the initial launch 2 years ago.
Okay. Yeah. So essentially, yeah, you're right that we've been speaking about Falcon in other public forums as well, right? Like we contributed the specification to the OCP. So I'm assuming that's the talk which you're referring to, right? So I think the external talks which we've given before were pretty high level, right? And it did not go into the technical details of what the technology is. And that's what the SIGCOMM paper gets into, right? And there have been quite a few advancements as well since the initial mentioning of Falcon at the OCP summit a few years ago. But more specifically, what has changed is essentially our experience in production, right? Like the paper essentially goes into details about how we've made this run in production and what we are seeing with real world applications and at scale, right? And that's what is different in this paper, apart from all the other technical advances with respect to how we are doing reliability, multipathing, and all of that. Yeah, so that's the key difference. And this is the first time we are talking about the details of the technical aspects for the first time. Like the OCP summit was pretty high level. Yeah.
Okay, thank you. Let's move to the next part, Vietnam part. Professor Hong Minh Tran, do you have any question? Your group has any question on Falcon paper, please?
I'm sorry, this paper we had no question now. Okay, I'm sorry, can you hear me?
Yeah, we can hear you. Looks like there's no question from there.
Sorry, this paper is Vietnam, we had no question.
Okay, then let's move on to the Indonesian part, please. Is there any questions on this paper, Falcon?
Okay, thank you for your time. Yeah, I have a question for Dr. Arjun. So good morning there, Dr. Arjun. So thank you for your time. Early morning, wake up and meeting with us here. Thank you very much. Okay, so actually I have two questions about the Falcons. The first one is regarding the because we know that the Falcon has a feature like congestion control feature, as well as it handles the multipath, something like that. So I just want to know like whether the Falcon also experiences such as a head of line blocking problem as TCP experienced. So that's my first question. The second one is about like because we are adding more functionalities in the NIC card. So just I want to know like the complexity. So how complex the NIC will be if all those features are really implemented into the hardware. Thank you.
Yeah, great questions. Right, for the first one with respect to head of line blocking, anytime there is resource contention or any sort of contention, right, there can be head of line blocking, right, and you need to take care of it. So with respect to Falcon specifically, where head of line blocking can happen is, as in the paper we mentioned, or in the talk we mentioned, that we introduce on-NIC resources, right, to handle out of order packets as well as to do retransmissions in hardware completely, right? You can imagine that these resources are finite on the NIC, right? And we can reach a scenario where you can have slow moving connections actually use up a lot of these resources if you don't do proper head of line blocking management. And that's something which we tackle in Falcon by actually doing congestion aware back pressure into the ULPs, so that the Falcon resources actually are being utilized in such a way that you don't have one single connection which is using up all the resources and is causing head of line blocking to the other one. So that's something which is there in the Falcon paper. I didn't go over the details of it in the talk in the interest of time, but it's in the transaction layer of the paper. So that's one thing with respect to the first question. And what was your second question?
How about the complexity
Complex,
of the
right?
hardware then?
Yeah. So that's a great question, right? Like with the other alternative is to do it in software, right? Like software gives us a lot of flexibility, but there are limits with respect to software stack scaling, as we've discussed, right? So pushing it into hardware is really a need to meet the demanding workloads. And complexity, like there is complexity, right? But if you design the hardware in a proper manner, right, like where you have clear division between the various components in the hardware and the entire NIC pipeline, and you define the interfaces properly, then you can actually individually test the various hardware blocks and make things more easy. So I think that's what we got right with Falcon, where the way we designed the various blocks, and we had a clear separation between the TX and RX pipeline, as we discussed in the hardware section of the paper, that helped us to actually manage the complexity with respect to implementation and getting it right the first time. But the other aspect is that given that hardware is complex and we can't really change it, right? But what our experience has shown is that we want some flexibility so that we can evolve the transport even after the hardware is actually taped out and is back with us. And for that, we introduced the Falcon Adaptive Engine, right? Which essentially does an intelligent split between pure hardware and what is running, say, on the cores in the smart NIC or a foundational NIC, right? And that gives us the flexibility of actually managing some of the complexity and do evolution even after the hardware is back with us.
Okay, thank you. I have one additional question actually.
Yeah, please go ahead.
So, like Falcon has like a very more like multiple ULP, multiple ULP on top of its layers, and then it also has a multiple path as well. So I just wonder that how Falcon does the scheduling things inside the implementation.
Yeah. So with respect to the ULP, right, the ULP designers can decide how they want to send in transactions to Falcon. Typically, it's some sort of QoS aware scheduler, which takes into account user priorities, right? And it also has, like, essentially it's some sort of weighted round robin scheduler. But inside Falcon, right, as you rightly said, it also does support multipathing, right? So the scheduling policy which we have there is that it's congestion aware multipathing. And what we mean by that is essentially that it prefers paths which have more available bandwidth, right? And that is actually inferred naturally because the C-wind will open up for the part which has more available bandwidth as we start sending traffic to the fabric. Right, so that's how we do scheduling inside Falcon within multiple parts of a connection for multipathing. Yeah.
Okay, thank you, Dr. Raju, for your.
Thank you.
Thank you. We'll pass on to Philippines. Dr. Manel, you have a question for Falcon paper.
Hi, can you hear us?
Yes.
All right. So, Arjun, thank you very much for accommodating us. Right? We just want to ask, if, let's say, if we want to this one, let's say, the transport, hardware transport, how complex it is for us. Let's say, we do it in a general purpose computer, or let's say, microcontroller. Let's say a prototype.
Sorry, is your question as to how complex is it to implement a hardware transport in software?
Hardware transport, yeah. Hardware to implement hardware transport in a general purpose computer or microcontroller.
Yeah, so with respect to implementing Falcon in any general purpose computer, yeah, I think it's a good idea, and I think it can be done, right? Like again, there we'll have to be careful about how much CPUs do we use for actually implementing the entire transport, right? Like for example, as a cloud provider or as an infrastructure provider, you would want to minimize the amount of resources on the host you use to actually run your services, where transport is also something which you have to run as a provider, right? So essentially that's something which we'll have to take care of. But fundamentally, from a transport standpoint, right, like nothing prevents Falcon from being implemented in a software. For example, there have been a lot of software transports which the academic community has spoken about at SIGCOMM or other venues over the past so many years, right? One thing which stands out is Snap or Pony Express, right? And one can think that we could take a similar approach and actually implement Falcon there instead of the transport which it has. So it's something which is worthwhile exploring. Yeah.
Thank you very much, Arjun. Thank you.
Thank you. Is there any more question from our part?
I still have a lot of questions to you. So, my second question is, from the congestion aware that Falcon Adaptive Engine can select a path to destination per packet, right? Is your feature. So, how to decide the best path based on your ACK information?
Yeah, so that's a good question, right? At a high level, what Falcon does is that it essentially does congestion control on a per flow basis or a per part basis. So essentially, think of this as acknowledgements come back, right? Falcon at the initiator or the sender, right? Like it generates events on a per flow basis because an ACK is associated with a flow or a path, and using that information from the signal, using those signals from the network, right, on a per part basis, the Falcon Adaptive Engine can run the congestion control algorithm and figure out how much available capacity there is, right? So for example, it's going to do per part congestion control. Like one heuristic can be that it essentially does per part congestion control. So it'll know how much sea wind is there for each part, right? And then it actually gives that information to the data part. And then the actual hardware can use that sea wind information to actually schedule packets along those parts. So that's how it is congestion aware. So essentially that is with respect to part scheduling, right? And with respect to, and that happens in the hardware data part, right? With respect to part selection, like if say we have to choose 4 parts, right? Assuming that multipathing, it's doing multipathing across 4 parts, essentially it'll use heuristics like protective load balancing to actually figure out which is the if the existing path is not good enough, then it's going to find another path by changing the flow label.
Vietnam part, please go ahead.
Yeah, can you hear me?
Yes.
Okay. That's a very specific impactful solo, but in second level catching design, the paper is mentioned implementing is a lot of second level collection state across the multiple IP block. to relation with latency and bandwidth. So could you share more about detail about the design choice? For example, with the size, requirement policy, but the sharing across the IPU block. Is that okay?
Sorry, I can't hear you clearly. If the moderator,
My question is, could you share more detail on this design for the second level base design? The idea because it using for the sharing between the IPU block, the which changes it.
the moderator, can you use your mic and repeat the question if you can hear it, and that way I can probably answer it.
My question is focusing on is the second level catch design.
Or could you please type in your question in the chat?
Okay.
That would be helpful. Thank you.
Okay, I will type in with this select. You can see here.
Okay. Do you want to?
That already this is my message.
Okay, gets back to me. Okay, next question is, can you tell me more about your decision that you choose Intel IPU card instead of FPGA card? Why? Is it-
Yeah. That's a great question, right? And something which we thought about for quite some time. And the reason why we took FPGAs, we did not take FPGAs, is typically our experience has shown that the operate and the latency requirements which we have, right? It's much higher in FPGAs rather than building like a foundational hardware IP block, right? A hardware block of Falcon. So that was one aspect, right? Like where the operate which we were targeting was like 120, 150 million ops per second, and the latency was like 3 microseconds, right? And just trying to achieve those high operate and low latency on FPGAs is challenging. And the other aspect was with respect to like the amount of cost as well, right? Like the total cost of ownership, essentially, with respect to FPGAs is much higher as opposed to the approach which we took, right? And as like a provider of these NICs inside Google, right? That's something which we have to consider with respect to CapEx and OpEx. So that was the other reason. Yeah.
Okay, thank you. So can you provide me more about your FPGA card model? Because I'm doing my research project with FPGA card too. So
I see. Yeah. So the thing is that for FPGA, right, we did not go ahead to actually really implement Falcon in an FPGA, right? But that's something which is but that's something which I think is an interesting direction which the community can also take. Like I think it's a useful direction for the community take with respect to trying to implement Falcon on an FPGA. Yeah.
Researcher at Vietnam side already typed in their question in the chat.
Oh, yeah. Taking a look. Oh, is it on the Slack chat or?
On the Zoom chat. Oh, on the Slack. Okay, on the Slack chat. I'm sorry.
Oh, one second.
SIGCOMM 25 SEA part.
SIGCOMM 25. Oh, SIGCOMM 25.
On the second level cache design, the paper mentions implementing a larger second level connection state cache shared across multiple IPU blocks to mitigate mesh latency and bandwidth pressure. Could you share more details on this design choice or idea? For example, size replacement policy and how sharing across IPU blocks affects fairness and isolation between workloads.
Yeah, so that's a great question. So the approach which we took with Falcon was to have like second level caches on the NIC itself rather than on the host, which is how typically folks deal with second level of caches. And the reason for that was that we again wanted to deliver predictability, right? And actually involving the host with respect to caching was something which brings in a lot of unpredictability given our prior experiences. So we actually had a second level cache on the NIC itself. And with respect to sizing it, right, like we size the caches based on the scale we want to support, right, like with respect to the number of uh, simultaneous connections as well as the RTTs which we want to target, right? Like, so as we mentioned in the paper, we took the bandwidth delay product into account to actually size some of these caches. And with respect to isolation between various entities actually using these second level caches, we essentially, it boils down to resource provisioning. If we provision the resources appropriately such that it can scale to the needs of the various blocks of the IPU, then we should be fine. So for example, the bandwidth to actually talk to the second level cache needs to be provisioned appropriately, right? So based on the scale which we wanted to target, right? Like you essentially size that appropriately and provision enough bandwidth. So that's how we went ahead with it. Yeah.
That's it. Thank you.
Okay, great. Thank you very much, Arjun, for taking your time to meet with us and discuss questions and help answering our questions for that.
Yeah.
Let's move on to the next paper, Fly Scalable Ultra Accurable Clock Synchronization for Data Centers. Thank you, Yu Liang, for joining us. So let's start the question from Indonesia part, perhaps. Do you have any question for this paper, Fly?
Okay, thank you for your time. Good morning, Yulia. How can I call you? Sorry.
You can call me Yu Liang.
Julian, yeah, okay. So I have one question regarding the channel that used by fireflies to exchange the probing message. Do you require to use like a special dedicated channel or just use it in general for network, something like that for exchanging the probing message?
Yeah, the Firefly doesn't require a separate channel or separate network. So all the probes of Firefly are sent towards the same network that normal packets, normal traffic is going through.
Okay, so it means that it can experience such like congested with others traffic, something like that. So it may cause some like delivery delays, something like that. So how do you handle such kind of problem?
Yeah, that's a good question. So yeah, definitely in the shared network there can be congestion, queuing, etc. So in Firefly, if you can check the section 5, we have several techniques to filter out those queuing delay, those jitters caused by queuing and etc. So on a high level, there are two approaches. One is software, another is hardware based. The software based use MinRTT as the reference to filter out packets. So for example, if some packets its RTT is much higher than MinRTT, we know it has queuing, right? But if packet doesn't have queuing, then it should be very, very close to MinRTT. So that's a signal we can use to filter out the queuing delay. Yeah, the second approach is using the commodity hardware feature called transparent clock, which was part of the standard PTP and have been supported by a lot of switch chips. Yeah. So yeah, with that, this feature allows the switch to write the total in-switch delay into the packet header and sum them up, right, in the same header. So when the packet reach the destination can by looking at that field, it knows how much total time it has been spent in all the switches. So if there's queuing, that number will be higher. So we can subtract that and get a no queuing measurement.
Okay, thank you. Thank you.
Thank you. Let's move to Vietnam pod. Do you have questions for this paper?
Yes, I have a question. It's the approach of the decoupling internal signal from the external signal to the layers synchronization is very innovative. So what is the external accuracy to the UTM? Is it what size millions signal level? Or the conversely symmetrical better? And how was the impact the branching of Firefly provide for both the internal and external synchronization?
Sorry, your maybe your speaker is a bit unclear, Mike. I mean, so I can't hear you clearly.
Could you please type in the Slack or in the chat in the Zoom, please?
The SIGCOMM is a layerless synchronization, so it's divided by the internal synchronization and the external synchronization. So, my question is if the external synchronization better or the worse than the linguist you provide in the paper now? And my question is, and how Firefly may adapt this condition? Is much clear? Not answer for you.
What I hear is that you are saying the internal synchronization and external synchronization, the separation of them, right? And but I still didn't get like the latter part of your question. Like you have compared to something worse or better or something.
There's a question in the Slack channel. And
okay, yeah, but I couldn't join the Slack channel.
Okay. I'll read it.
Yeah.
Firefly ultra accurate clock synchronization for databases. Your approach of decoupling internal sync from external sync through layer synchronization is very innovative. What if the external accuracy of UTC is worse than microsecond level, or conversely significantly better? And how would that impact the guarantees Firefly provides for both internal and external synchronization?
Okay, got it. Thanks for the question. Yeah, so that's a good question. So you are basically asking, what if I assume you're asking if the time server, right, the proxy of UTC for the co-cluster, if the time server has much higher error. Yeah, so we have evaluation in section 6.4, 16.5, where we have evaluation of the layer synchronization, how it works and how it protects against different level or even higher level of error from the time server. So in there, we have injected up to 160 microsecond worth of jitter into the time server, meaning that all the time stamp coming from the time server, right, it will randomly moved by 160 microsecond. And even with that level, the internal synchronization is still very low, right? If you look at it. Sorry, someone is speaking?
Yeah, that's okay.
Okay, yeah. So even in that case, right, the internal accuracy is still pretty good.
Yes.
So this because our design of the layered synchronization, right, is in a way that try to decouple the internal sync accuracy from the external sync. Yeah. And also, if you really have a very, very low quality time server, right, even worse than the 160 that we injected, which I believe is very rarely the case, but even if that case, you can still tune the parameter of the layer synchronization, right, to make that even gentler than being used. So yeah, basically you have you have a knob to tune the algorithm to always protect the internal synchronization, right? And the trade-off just maybe converge to a time server slower, right, in an effort to protect against its error.
Yeah, thank you very much for the response.
Thank you. Philippines pod.
Professor, we don't have any questions for this paper. Thank you.
Oh, Vietnam pod, do you have more questions?
Yes, I have one more question, please. Following the last question from Professor Ming, I want to understand more earlier about the synchronization. In the case that yeah, any state about the synchronization in case of experiment. So how about in case of the data center with the number of device is get large and large, get more and more. So how about the accuracy about that?
If I understand correctly, you are asking about the scalability of Firefly. Like if you have more devices, more clocks in the cluster, how does this accuracy change over larger size?
Yeah.
Okay, yeah, that's a good question. So yeah, so I think I also touched a little bit on in the talk on the scalability. So the scalability, we have a theory proof that shows that the scale, the graph, right? In the graph, every clock talk to other random graph, other random clocks. So as long as D scale as O log n, it will achieve the same level of accuracy. So basically, yeah, you can have more clocks, then you just only need a few more peer clocks every clock talk to, right? Maybe one or two, yeah. Yeah. Also, we have evaluation in that try to evaluate different sides of the cluster, and it shows that the accuracy is almost the same level. Yeah.
Are there any more questions from Indonesian pod?
Okay. Is my sound quite clear?
I can hear you. Yeah.
Okay. Okay. Thank you for your paper and research. From your paper, I found it quite impressive that Firefly achieved nanosecond level accuracy on community hardware. But I'm curious, in practice, what do you think will be the main challenge for deploying it widely in real data centers? Is that like more about the hardware support, the network variability, or the operational side?
Thanks for the question. So I'm asking, what's the main challenge of deploying Firefly in a data center?
Yes, yes.
Okay. I think that's a good question. What's the challenge? So first of all, I also manage solutions like PDP, right? And I find Firefly is much easier to deploy than PDP because PDP require a bunch of hardware support, but Firefly it's mostly software driven. Right? So I think if I have to name some challenge, for example, you need a hardware timestamp from the NIC. That's needed for any high precision clock synchronization solutions. Yeah, so basically Firefly is not using more support than other thing requires, but yeah, it does need hardware timestamp from the NIC. And this feature has been available in many NICs, but on older NICs, it may not be readily available. Some NICs, the driver may not support it, so we have to change the driver to expose the timestamp. Hardware supported it. The driver was not ready, so I have to change the driver. Yeah, but other than that, yeah, I don't see much challenge. You can it's software, right? So you can deploy it.
Okay, thank you so much for the answer.
Thank you very much. Is there any more questions for the two authors? I don't know if the author for the third paper is here. Saisal? Okay. Are there any more questions for both authors, like Falcon and also Flyflies?
I have more question for the Falcon works, so I'm not sure that he sleep.
No.
Oh, okay.
Go ahead.
Oh, thank you,ครับ. I'm not sure that this work still based on Ethernet structure and UDP, or you change something or not.
So on the wire, it is essentially a UDP. Like the headers are, it's encapsulated using UDP, right? And the paper goes into those details and the spec as well, which we've essentially released as well. So on the wire, it's essentially like an Ethernet packet, and we encapsulate the Falcon specific headers as well, right? Which the receiver and host can actually use to decipher it and actually handle the Falcon logic. So on the wire, it's like a typical Ethernet packet. Yeah, UDP packet. Yeah.
Okay, so you said that means you didn't modify any Ethernet or UDP structure, right?
I mean, we introduced Falcon headers, right? Like essentially, for example, for reliability, Falcon has its own ACK format, or every packet which we send out has like a Falcon base header, which will identify what kind of transaction it is, the PSN, the RSN, right? Like all of that is custom Falcon information, which needs to be sent from the sender to the receiver, right? Like, so essentially, there is like a specific Falcon header which we put into the packet, right? Like, so that's how we do it. Yeah.
So there's a lot of information that FAE need to read it. So how about the overhead?
Oh yeah. So FAE doesn't need to actually read the entire information, right? Like what actually happens is that we have like a packet comes in, right? Like with respect to FAE, right? Like it gets events when, say, you receive an ACK or a NAC, and when you actually have a retransmission event locally, right? So when an ACK or a NAC comes in, right? Like what actually happens is that you don't forward the entire packet to FAE, right? Like the hardware has the capability to look at relevant information and actually only give that to FAE, right? Like, so we have like a program, we have essentially the hardware logic to extract the necessary information, which FAE needs to do the various algorithms it runs, right? Like, for example, the 4 timestamps, T1, T2, T3, T4, or the receiver buffer occupancy so that it can modulate and receive it appropriately, or CSIG value from the network, right? So essentially the way it works is once we receive an ACK packet, the hardware, or essentially the packet delivery logic, which is in hardware, extracts the relevant information and sends it across to FAE in the event format, which you've described. Yeah.
Okay, thank you. Okay. So I want to know about the ULP layer. Why your default supported protocol is just only RDMA and NVMe. This is related with the Intel IPU supported protocol also.
So if your question is why did we support only those two ULPs, because that's the applications which we wanted to tackle, right? Like for example, RDMA is required for the reasons I mentioned in the talk to break past the scaling barriers of software transports, right? So RDMA was a natural use case which we had to do. And with respect to NVMe, again, we have storage use cases where we wanted to be able to offload the NVMe logic to hardware, because otherwise it adds in a lot of overhead. Typically, the way people do NVMe is it's NVMe over fabrics or NVMe over RDMA, right? But there's the semantic mismatch between NVMe and RDMA. RDMA traditionally, as is done in Rocky Nix, is an ordered protocol, but NVMe is unordered. And when we do NVMe over RDMA, you're unnecessarily layering an unordered protocol over an ordered protocol, right? So even from a semantic standpoint, it made sense for us to have the NVMe ULP. So that's the reason why we went ahead with those two ULPs, right? But that was the reason we wanted it to be extensible, right? Like Falcon is the transport, and it should be able to support various other ULPs. So we have designed it in such a way that the interface which Falcon exposes is something which other ULPs can use and actually implement. Yeah.
Okay, so from my understand, this work implemented on the custom Intel IPU E2100, right? Or it's just a vanilla Intel IPU?
No, this is like a new IPU which Google Intel work together on, right? Yeah.
Okay, I have that just two more questions. So the first is, how about your fairness policy for the Falcon? Because I read the paper and the figure 13 is looks like that your fairness policy is try to equal every connection bandwidth.
So with respect to fairness, right, like we have different schedulers in the ULP itself as well as inside Falcon, right? So I can focus on Falcon. So inside Falcon, we have like a scheduler, which is like a weighted round robin scheduler. And as an operator, you can decide what weights you want to give to different connections, right? So when you bring up connections and you set it up, you sort of know what priorities are for different users, right? And you can translate them into the connection scheduler of Falcon, right? And so that gives you the flexibility. Like we've built a scheduler which is QoS and user priority aware. Yeah.
So, okay. The last question is, you said to me that you try to implement on the FPGA and you face a lot of struggle and a problem.
So let me clarify there, right? Like, so it's not like we tried to implement it in the FPGA, right? Like essentially when we started out on Falcon, right? Like we wanted to decide what option do we have to go with, right? Like, do we do FPGA or do we do like an IPU based one, which is not FPGA based, right? Like, and essentially by doing analysis, right? Like to meet our requirements, we realized that an FPGA, even the best FPGAs on the market are not going to be able to meet our requirements. So from the get-go, essentially both from a performance as well as the TCO standpoint, FPGAs did not make sense for us.
Okay, so can you provide list of the data and graph render code that you use to generate in the paper figure? Because I read your entire paper and I still question with some figure that how this the lines to be like that. Yeah.
So we've open sourced the simulator, which was used to generate like some of the results in the paper, right? So that's something which you can actually just go download from GitHub and actually play with it, right? And so that's something which the community can use, and we hope the community actually uses that and improves, pushes the frontier with respect to hardware transports, right? And with yeah, so that's what we've revealed. Yeah.
everything included in your Falcon GitHub, right?
Yes.
Okay, thank you so much,ครับ.
Is there any more questions from other parts? Well, if not, then on behalf of the pod moderator, I would like to thank you. We are very grateful for Arjun and Yuliang that taking the time to have a talk with all of us in the other side of the world, and we really appreciate SIGCOMM reaching out to include us in the venue as the pod in Southeast Asia. And thank you, Dr. Sucha, for contacting speakers and gather the speaker for all of us here in Southeast Asia. Thank you so much. And again, hope you have a great time there and we'll watch the videotapes. Thank you so much.
Thank you.
Thank you very much.
Thank you, SIGCOMM, too.
Thank you so much. Thank
Thank you very much,
you.
Arjun
Bye-bye.
and Julian, for
Thank you.
helping this. Thanks.
Yeah, no problem.
It's very helpful for us.
Thank you.
Yeah. Okay. Yeah. Okay. So
Let's take a picture. Could
Oh.
you please sorry, before everyone leaves, could you turn on your video camera again and let's take pictures together? Okay. ค่ะ everyone's coming in นกกถ่ายให้หน่อย Okay ไม่ค่ะอาจารย์
Yeah, so while we are waiting, so let me maybe talk about the other authors that cannot come today. So most of them are like from China, and it turns out that somehow they can leave China only 5 days. Somehow, so that's why today morning they have to like leave and go back to China, and that's why they cannot join.
Again, thank you so very much and see you guys again. Bye.
Oh
Have
yeah,
a great
thanks for that. Okay. Bye.
Bye.
Yeah, thank you very much.
Thank you very much.